In this section, we will analyze the belt drive's working condition. This figure illustrates a typical open belt drive with pulley or sheave diameters of D1 and D2 and the center distance A. From this illustration, we can calculate the small pulley's contact angle alpha 1 as equals pi minus 2 theta. As a result, the following contact angles are determined in degrees as theta equals sine theta equals d2 minus d1 divided by 2a. One of several elements affecting a belt drive's ability to transmit power is the contact angle. When the speed ratio is 1, only then is it equal to 180 degrees as no speed change. The small pulley's contact angle is always less than or equal to 180 degrees or pi rad. That's alpha 1 equal 180 degrees minus d2 minus d1 divided by a multiplied by 57.3 degrees. And for determining alpha 2, 180 degrees plus d2 minus d1 divided by a multiplied by 57.3 degrees. The belt is first mounted by loosely surrounding two pulleys with a smaller center distance. Then the two pulleys are separated to the chosen center distance. As a result, the belt has an initial tension of F0 and clamps securely on the pulley surface. Since it guarantees the belt will function effectively under design loads, the initial tension is crucial. At the point where the belt and the pulleys meet, normal force N is generated in the radial direction as a result of the initial tension F0. The belt exerts friction force on the driving pulley in the anti-clockwise direction when the driving pulley rotates at a rotational speed of N1 in the clockwise direction. In exchange, the driving pulley exerts the same friction force, F subscript F, on the belt in the opposite direction, in the clockwise direction. As a result, this friction force drives the belt. Similar to how it rotates around the driven pulley, the belt's friction force acts in a clockwise manner on the driven pulley. The driven pulley is driven by this force and rotates at a speed of N2 because the frictional force acts as a tangential force. As a result, friction serves as a valuable tool for power transmission in belt drives. Tensile force in the bottom strand of the belt increases from initial tension F0 to tight tension F1 as the belt moves from start up to operating speed, while the tension force in the top strand decreases from initial tension F0 to a lower value of F2, known as slack or loose tension. Likewise, the lower strand of a belt is known as the tight side, while the higher strand is known as the loose side. The flat belt element that a radial force Q is exerting on a pulley is shown in this diagram. The flat belt working surface's frictional force is F subscript F equals F multiplied by N equals F multiplied by Q. Without considering friction in the radial direction, the bottom left picture shows a section of a V-belt acting on a sheave with the same amount of radial force Q. The frictional force on the working surfaces of the V-belt is F subscript F equals 2Fn equals F divided by sine phi over 2 multiplied by Q. This is Fv multiplied by Q. Because of this, a V-belt drive's equivalent coefficient of friction, Fv, is obviously higher than a flat belt drive's equivalent coefficient of friction, F. The wedge effect is what is meant by this. V-belt drives offer a greater overall power transfer capability than a flat belt drive in terms of both low cost and space because of the increased friction brought on by the wedge effect. For ease of use, the study that follow will focus on flat belts. The friction coefficient is replaced in V-belt by Fv. Then Fv equals F divided by sine phi over 2 as stated in the previous equation. Assume that the belt's overall length remains unchanged. Therefore, F1 minus F0 equal F0 minus F2. The length of the belt increasing on the tight side is the same as the length of the belt decreasing on the loose side. As a result, the initial tension is as follows. F0 equals half F1 plus F2. When we add up the torque with regard to the driving pulley's center, we get summation of T equals F subscript F d1 over 2 plus F2 d1 over 2 minus F1 d1 over 2 equals 0. The total of the distributed frictional forces at the belt and the pulley contact determines the effect of tension on the belt drive, which is linked to the pulley torque. F subscript F equals F1 minus F2, then Fe or F subscript E equals to F subscript F equals F1 minus F2. When barrier equations are taken into account, the tight tension F1 and the slack tension F2 are provided by F1 equals F0 or F0 plus Fe over 2 and F2 equals F0 minus Fe over 2. A belt's P or power transmission capability is as follows, equals F subscript E multiplied by V divided by 1000. Therefore, an effective tension Fe or frictional force Ff between the belt and the pulley must be ensured in order for the belt to convey power P at speed V. In other words, the belt must be kept at a low initial tension. In conclusion, the frictional forces that are dispersed at the belt-pulley contact make up the effective tension Fe. It also matches the variation in belt tension between the two strands. The power transferred increases with the difference in belt tension. It is vital to ascertain the maximum frictional force or the maximum effective tension because the frictional force has a critical or maximum value that restricts the amount of power a belt drive can transfer.